Okay, so I will start. Um, so we have discussed now a lot of theory, and it's sometimes difficult um, to understand all the theory without any proper application. Um, so therefore, we have decided, Professor Sahu and me, to have here's two lectures about numerical simulation for combustion model using Cantera. So a lot of the details, especially concerning numerical modeling, will be explained in lectures which will be held maybe on Friday or next week. So some of the fundamentals may still be missing, but the advantages of Cantera is that if you want, you can install it on the fly today and start with some practical simulations, play with the details here, which hopefully helps you to understand all the fundamentals we have explained until now and which will come in further lectures. So I've started to study combustion in 1995. In my master's thesis, I simulated the laser-induced fluorescence of OH radicals in a flame. And then with my PhD thesis, I started to simulate ignition processes and flammability limits using 0D and 1D models, incorporating detailed chemistry. Why is this so important? So in nowadays we are talking about exascale computing, so the computational quantities are getting better and better, and we can try we can simulate complete gas turbines in our computers today, but this of course is still very expensive concerning computational cost, and if you want to learn something most often 0D and 1D calculation are still the best tools, because within seconds, maybe minutes, you can vary a lot of parameters, and you can examine the influence of, for example, changing the hydrogen content in your mixture. Does it increase the flame velocity? Does it increase the pollution formation? So within very short time you can examine a lot of parameters, and therefore it's a very valuable tool. So I have done this, as I said in my PhD thesis, with an in-house code written by my supervisor in Fortran. I'm still using this program because I know a lot of details, and if I want to change the code, I know how to handle this. But there exists a lot of in-house codes for these kind of simulations, and there are also existing packages like Chemkin, which is very popular because a lot of the mechanisms you can find in the literature are given in a Chemkin format. But I think a very popular open source solution we can use in our days is Cantera. It has excellent examples, and so the most complex thing using Cantera for me is the installation. Until it runs, until all libraries are included, So I'm sitting behind a firewall after I get access to all the things I need. That takes a lot of time, but when it is running, it's a very stable and very comfortable solution. Therefore, I want to present it here because, as I said, after this lecture, you can go home and install it directly and then play with it. So it's an open source tool that can be used either in Python, MATLAB, C++, or Fortran 90 for problems involving thermodynamics, kinetics, and transport processes. So the advantages, so the chemical, kinetic, thermodynamic, and transport calculations are automated by Cantera. So you can easily, very easily, incorporate detailed chemical thermokinetics and transport models. That's a big advantage. So you have heard a lot of fundamentals. We need proper thermodynamical data, for example. We need proper reaction mechanism and so on. This can be found in literature, and this can be found in proper format for Cantera, or you have tools to translate it, for example, from Chemkin. So you don't have to bother about this part. You just can use it and learn a lot, and you don't have to bother about so many numerical problems because it's very stable. I focus here on the Python realization because the advantage here is the post-processing to the production of proper output is very easy, as the proper libraries are installed here, and it's quite helpful. Again, so if I, for example, have to review a paper and I have some question marks, a lot of things I can easily simulate using such a simple tool, and within minutes I get the information I need. For example, is the velocity really increasing, the flame velocity, when I increase the amount of hydrogen in the mixture or not? Some things you can easily check without too much work. So I will not go here into the details, but there are excellent tutorials for Cantera you can find in the internet. So I have given the links necessary here. So there are different ways to install Python, Cantera in Python. So I don't go here into the details. It's just for your reference. Actually, for me, most complex thing is here the installation of Conda. As far as I know, the Anaconda distribution is eventually no longer supported, or I'm not allowed to use it behind our firewall. But the Miniforge installer solution works quite well, and this is the one I recommend here. So, and for our discussion today, I just have two examples. When you go to the webpage of Cantera, you find a lot of reactors you can use, and a lot of tutorials, a lot of examples, and I just will focus on two realizations here. But I think if you understand the principles, then it's easy to use any other reactor, any other class in Cantera to examine your specific problem. So I will focus on the batch reactor, so Cantera ideal gas reactor class, and on laminar burning velocity, how to calculate laminar burning velocities using the class Cantera free flame. So you can find a lot of reactor types in Cantera. So Professor Sahu has shown you yesterday some reactors, constant pressure, constant volume. So we are talking about 0D simulations here. So you solve your equation as a function of time, but there are no spatial dependencies. So the assumption here inside this reactor, everything is homogeneous. So there are no derivates in any of the coordinates. Everything is homogeneous. So you just have to describe your equation system or the dependency as a function of time. So you can have different reactors here. So for example, here we see a continuously steered tank reactor. It's a homogeneous reactor. You have several variables which can describe your system. And in this case, you can have an inlet and an outlet. So a specific defined inlet flow with specific mixture composition, temperature, and pressure enters your vessel. Chemistry takes place, and then depending on your reaction and temperature and so on, you have a specific outflow. And so you can focus here on the boundary conditions you want to examine and the specific inlet conditions you want to examine. We can use such a setup also, or you can find it in the literature under perfectly steered reactor, and it can be used also for jet steered reactors, which the specific reactor we will learn, or we'll get some more information about this tomorrow. But I will go back to this batch reactor.
Sir, could you have some examples on those reactors?
Pardon?
Could you have some examples on those reactors, some real life applications?
What do you mean with examples?
Examples of batch and continuous steer reactor and perfectly steered reactor, bridge steer reactor.
Okay, so these three here are represented by this image. So you have a 0D system, homogeneous system, where you have some inlet flow and an outlet flow. And you can define your boundary conditions here, and you can define your inlet conditions. And I will explain it with the batch reactor more in detail what I mean here. And maybe then afterwards you can please ask again if something is missing. So the system, the two most simple system Professor Sahu has given us yesterday were the constant volume reactor and the constant pressure reactor. That means you have a closed system filled by your homogeneous gas mixture, and then you, at a given pressure and temperature, and then you solve your set of governmental equations. So in case of constant volume, you say, okay, volume is constant, temperature increases, number of moles is changing, so temperature has to change. Pressure has to change when we look at the ideal gas law. Volume is constant, pressure has to change. If you have a constant pressure reactor, the volume is changing as a result of your chemical reactions. So, and here in this example, so we will learn all the numerical details next week. But but we consider here 4 state variables: the mass, the reactor volume, the temperature inside, and then for all the species we have one equation concerning the mass fraction of the species. And the advantage of the constant volume reactor is the total mass stays constant. There is no inlet, inflow, no outlet, so no change in total mass. So of course we neglect any wall reactions and so on. So it's just an homogeneous system, and the volume is constant, so there is no change in volume. And the energy equation is represented here with the temperature. You can normally find this also as represented by the inner energy, sometimes as using the enthalpy, but here we use the temperature, and the temperature change only depends on the chemical reaction, the heat, the chemical energy transferred to heat energy, or transformed to heat energy. And then of course we have a change, temporal change of mass fraction here, and this depends on the chemical rates we have, this omega dot. This is described by our chemistry, and WK is the mole fraction at a specific time. So it's a quite easy system, and at the end we have a change in temperature and we have a change in mixture composition if you use this simple setup. And it's really simple. We talk about seconds. Even if you use very large, very complex reaction mechanisms, within seconds you can get your result. So it looks, for example, like this. You have, for all your variables in your system, you get the solution as a function of time. Again, it's a 0D simulation, so no spatial dependencies, no coordinates x, y, z, just the result as a function of time. Here, temperature, and for 3 selected variables, you can see the different behaviors. So the system heats up and reaches the final adiabatic flame temperature. So OH forms in the flame front, so after ignition takes place, and as due to the fact that we have a high flame temperature, we still see a lot of OH in our exhaust gas. Hydrogen is formed during the ignition process, the atom, hydrogen atom, and then it's used by the chemical reaction. So here ignition takes place and then it's reduced. And here, of course, it's a hydrogen combustion simulation. Hydrogen at the inlet, ignition takes place, hydrogen is consumed. All this information we get quite easily, and most often we are interested here in, for example, the ignition delay time. How long does it take at a specific inlet condition? So at given mixture composition, pressure and temperature for the system to ignite. How long is the time between 0 and this increase of a specific variable? Because when this is a quantity we can measure easily in our experiments. And what the kinetic guys do is they develop their big reaction mechanisms, and at the end they compare the calculated ignition delay time with the experimental one, and then they check, okay, I have some deviations here. I have 1000 elementary reactions. Which of them are really important for this specific problem? They can perform some specific tests and so on, and this we will discuss today, just to give you an overview of the tools we have without having all the details you need to understand, but of course this will come in following lectures. So here, ignition delay time. On the left you can see an experimental result from I think it's from an RCM, rapid compression machine. So we compress a system. That's the first pressure rise we have here on the left. We compress our system in this rapid compression machine. So when we compress a system, of course, temperature increases. So chemistry needs some time. Competition between the chemical processes and, for example, heat loss to the wall and so on. But then after specific time here, around 700 microseconds, the system ignites, the pressure increases. In this specific experiment, they also measured the chemiluminescence of OH radicals using an optical sensor. So you can see, okay, no OH, no OH, no OH, and suddenly you can see an increase of OH. So here ignition has taken place. And that's the important thing if you want to examine some work in literature, want to perform similar calculations to see is my mechanism good enough or so on. You have to use the same criteria for ignition. So you can find literature where they define the ignition delay time using the difference in the pressure signal. So here first increase, second increase, that's the ignition delay time. Here in this example, giving this paper here, they focused here on the OH signal. Maybe 50% of the maximum OH signal is defined as the ignition delay time. Or you can find in the literature something like this. So you examine the maximum slope of your OH signal, and then you use this line here to check, okay, at OH equals 0, here at that point, there is my ignition delay time. So you have a lot of different definitions. We will see it later. There are also some papers where they use the maximum. When the maximum concentration is reached, that's my ignition delay time. It's always important to use the same definition to compare your results. But again, ignition delay time is defined as the time between reaction starts and finally an ignition takes place. So, and here's one example as from a tutorial of Cantera. So we have this here ignition delay time as a function of 1 over T or 1000 over T. So temperature increases from here to here, and we have seen it yesterday. We would expect a linear decrease if we consider an Arrhenius equation, because we have a logarithmic scale here. However, we see this change of ignition regions due to chemical reasons, as we have discussed yesterday. So we have one specific regime here, then we have here another regime, and finally in the high temperature area this H plus O2 leading to OH plus O reaction governs the ignition delay time. So in here we talk about this negative temperature coefficient. Even though the temperature is increasing, the ignition delay time decreases due to chemical reasons. And in this paper here, they have performed numerical calculations and compared the calculations with the results. And in the tutorial, you can get this mechanism, do your own calculations, and compare your outcome with their paper. So what we need to do to perform such a calculation. So here at this link you can find this tutorial which I want to discuss with you. So, and if you have any questions right now, or you go home, try it at home, find some errors, of course we can discuss it later on. So it's a typical classical setup. First we have to load some libraries. You can use different integrated development environments, IDEs, so PyCharm, Jupyter. There are different possibilities to use Python. You can also use it directly. But first of all, you have to import some libraries here for data handling, and of course Cantera has to be included too. Then here we use Matplotlib for the output of our figures. Such a comfortable tool. So I have started with GNUplot, which is also excellent, but this is much easier to use. So you have a lot of functions to represent your results in a plot after the work you have done, and very, very easy solution. Okay, what we need? Okay, we have the tool, but of course we need the inlet data. And so in this example there is a mechanism given. Of course, when we follow this link here, we'll come to a web page where all the data is given in this classical ChemKit format. So we have the thermodynamical parameters, which we need for enthalpy, heat capacity, entropy for each species. We need to know this, of course. Then we have the transport parameters, which we need for heat conduction and diffusion processes. Of course, we have a 0D calculation here. We don't have to bother about this part. And finally, you can download the chemical mechanism. This is not the format we need. We need an YAML file. That's a classical input format for Cantera. And of course you can download this and find your own tools to convert this if necessary. But of course you can also find this specific mechanism already in a proper format. And that's very important. This has a specific format. You can define several phases. So for our examples today, we always only have one phase. And each phase consists of reaction species and elements. So we have a specific phase, then we have species, and then we have reactions. And these have a proper format. Normally you don't have to bother about it because you only use this. But of course, this has to be in a correct format, otherwise your simulation won't work. So for this example here, you can see 160 species as a list. The elements are given here, so nitrogen, carbon, hydrogen and oxygen. Some keywords here we don't have to bother about today, but so that's the definition of our phase. And then for each species we find the thermodynamical data we need. So we have here nitrogen. So then for the thermodynamical data, okay, specific model, temperature range. That's the way you normally find these data. You find 14 variables or 14 data points. 7 for the low temperature case, so in the range here 300 to 1000, and 7 for the high temperature case, 1000 to 5000 K. So, and these 7 data points are used then to describe or to calculate the enthalpy, heat capacity and entropy of your molecule, in this example, for this example, nitrogen. How this is done we will learn later, but this is the idea behind it. So we have the data we need to calculate the thermodynamical properties for all of our molecules. So we have everything we need here, and then at the end, of course, we need our reactions. So 160 species. I don't know how many reactions in total. And there are different types of reactions involved in Cantera, or this YAML file. I have just explained here 3 different formulations. Of course, you can find several more for specific problems. So the classical way is the modified Arrhenius form. So K is equal pre-exponential factor T to the power of B, and then the activation energy. So when we look here, we have this equation CH4 plus H gives CH3 plus H2. And here we have A, we have B, and we have the activation energy. So the 3 parameters we need to solve the reaction rate as a function of temperature for this specific equation. Then we have 3 body reactions. So you have asked yesterday this M, what does it mean? So here we have it, H plus CO plus M, a colliding partner, M, gives HCO plus colliding partner. This does not change. It just takes part in the reaction, but it does not change. So, and the colliding partners here can be H2, water, carbon dioxide and CO. And you don't want to solve this equation for each of the colliding partners, so you sum them up. So the total concentration of M you use in your equation is the sum of the concentration of the species in the specific volume and the efficiency. So the efficiency is given here by the numbers. So water is a very effective collider, and hydrogen not so effective. And finally, we also have, as we have seen yesterday, a pressure dependency. And here you can see a specific realization how to examine or calculate your reaction rate depending on the pressure you are using. So it's a specific realization. I don't want to go here into the details because it's something, it's very complex, and it's more easy to discuss it maybe again when we come again to the numerical part. For this tutorial, I would like to skip it because there are different possibilities here, but it follows a specific format. So you can calculate your reaction rate as a function of pressure and temperature at the end. So then, okay, we have imported our libraries we need for the calculations. We have our mechanism. Okay, then we need to say our tool, okay, at which initial conditions we want to perform the calculations. That means what is the temperature, what is the pressure, what is the mixture composition. So in this we have here, say reactor temperature, reactor pressure is 1000 Kelvin, 1013 or 1.013 bar, 1030 millibar, and we can, and that's really very helpful with the other tools I know. Compared to the other tools I know, you just use this function set equivalence ratio, phi equal 1, you define fuel, you define oxidizer, and he calculates automatically for you the mixture composition. So I don't know it for heptane here, N-heptane, what is the concentration at phi equal 1? I think it's something around 2 point something volume percent. But so this is done automatically. At the end you have the mixture consisting of N-heptane, oxygen and nitrogen, representing a mixture phi equal 1. So you can change your number here. Of course, you also can give the concentrations or volume concentration you want directly, but this is very, very easy to use it in this way. So we have everything we need. We have the initial condition of our system, we have the mixture composition, we have the temperature and pressure, and we have the reaction mechanism, so we can say solve the system. So this is done here. We call this class here ideal gas reactor, and we solve it as a function of time, or the result is then here in this vector here. But okay, then we have all the data to get the plots I have shown you. So at the end we have solved our set of differential equations as a function of time, and we have temperature as a function of time, and so on. But what we want to know is ignition delay time. So here in this example they have defined a specific function, and here ignition delay time is defined at that point where we get maximum concentration of a species, and the reference species here is OH. You can use, of course, any other species. Again, it depends on the criteria you can find in the literature when you want to compare your results with the one from literature. And then you just start the calculations, and here you call your function ignition delay time, which gives you then the ignition delay time tau. That's it. Quite easy. There is one important point here, the estimated ignition delay time. So when you, for example, want to calculate the ignition delay time of hydrogen in air at phi equal 1 from 800 to 2000 Kelvin. You, of course, change the ignition delay time by several orders of magnitude, from microseconds maybe up to seconds. And if your estimation is here too slow or too small, and your chemistry takes too long, you cannot find an ignition delay time. So you have to play with this number here if you want to get your ignition delay time. So do not get confused when there is no result. Most often this number was just too small. Your system needs longer than you have expected. So here then, until the time is smaller than the ignition delay time, he's doing the loop, and at the end he stops. Then, okay, here some specific information to perform at the end this nice plot. So here we have the ignition delay time, or we have a plot of the mass fraction of OH, and this point here, the maximum, is defined at the point for the ignition delay time. So for one specific configuration, pressure, temperature, mixture composition, we have now the ignition delay time. But when you remember the plot I've shown you, we have plotted the ignition delay time as a function of temperature. So of course we have to do this very often, and that's quite easy. You can define a list here. So we say here, I think there is an error in the tutorial. So I think from 1800 to 1000 we want to get the ignition delay time with a step width of 100 Kelvin and temperature of 975 to 475 Kelvin. We want to have a smaller step width, so 25 Kelvin. So for each of the points here, we want to get the ignition delay time. So then here is a vector which considers the change of ignition delay time as a function of temperature. So for the lowest temperatures, we say, okay, maybe 100 seconds is what we estimate. For the intermediate temperatures, 10 seconds, and for the high temperatures is quite fast. Of course, this is an estimation. At the end, you have to check, is it right or not, and maybe have to adjust it and perform the simulation again. But again, we are talking about seconds. The calculation itself is not a problem. So then you get the tau again for each configuration. We use the same mixture composition here, N-heptane in air, phi equal 1. And then we just have a loop over all of our temperatures we want to examine, and get for each temperature our ignition delay time. So we do not change pressure and mixture composition in this example, but if you want, you can also have a loop, additional loop about change of temperature and an additional loop change of mixture composition. Whatever you want, you are free to change it. At the end here we get a vector which for each temperature gives us or includes for each temperature the ignition delay time we are interested or we want to yield. So that's the output of the calculation. And finally, here are some details concerning the plot. So this is the outcome of our simulation, which looks not so bad when we compare it with the initial plot from literature I've shown you. So of course the mechanism comes from this paper. So you can see here, we also see this influence of the negative temperature coefficient. Within minutes, we can set up our system in a way that we can get the same results the authors have presented in the paper. So it's an excellent example for this specific setup. So, okay, now we have talked about the example, and that's a classical way. When I start to use Cantera, I take such an example and play with it. First, I do the same calculation and check, do I get the same results? Is everything working properly? And then, for example, I change the temperature, I change the pressure. So what is the influence? And if I'm confident then with my simulation setup, I use it for specific topics where I'm interested in. For example, we have done here some research of the dependency of the ignition delay time from mixture composition concerning ammonia air and ammonia hydrogen mechanisms, hydrogen air mixtures. And we were interested in the dependency of the outcome concerning several mechanisms you can find in literature. So ammonia is now quite popular in our days, and you find dozens of mechanisms, and you find dozens of papers, and each of this paper has its own favorite. So for their specific experimental condition, this specific mechanism was the best. So it's quite hard to say at the beginning which one is the best for our specific configuration. Therefore, we played with a different list of mechanisms here. They have, you see, quite different number of species, from 32 up to, or 31 up to 128 species, and a lot of also different number of reactions are included. So because all these mechanisms were developed for a specific aim. Then, okay, we also changed the mixture composition. So for this ignition delay time, we compared our results with RCM measurements. And here you see they have used quite high amount of argon and only very small amounts of ammonia and oxygen. But we have here 3 equivalence ratio from 0.5 to 1.5. So further details can be found here in the paper, in these 2 papers. But we were now interested, okay, we want to compare these mechanisms at these specific conditions with the results given in literature. So can we get the same results, or do we see something different? So so we have the same setup here. So we have to import our libraries. We have to import here also Matplotlib. Then, okay, for this example, I have here one specific mechanism from the list I've shown you before. Again, our specific inlet, starting conditions, temperature and pressure, 1630 Kelvin and 3.5 bar, following the literature we have. And here the equivalence ratio for this specific system I've shown you. So 90% of argon and ammonia and oxygen representing a mixture of phi equal 1. So everything again is calculated automatically here for us. So then here I've had the output for some of the results here, just to double check is everything correct here. And then I start my calculation, get again time history of all species, or and temperature and so on. And in this case, the reference species is nitric oxide, not OH as in the example before. And I have a different function here, that was the main work, because in the literature the ignition delay time was defined as 50% of the maximum. And so we have to use the same criteria in our calculations. And what we do here is, of course, first we find the maximum, then we find the next grid point near to the half of the maximum, and then finally we have an interpolation which gives us the time exactly at the half of the maximum. So then we have this, the same criteria in our simulation compared to the experiment from literature. So again, we start our calculation. We have to consider the estimated ignition delay time, and finally here we get our ignition delay time tau. So here, for example, I show you the time histories for a lot of different simulations. So it's phi equals 0.5, 1 and 1.5, and here you can see for all the different models we have used the NO mole fraction as a function of time. And you see, of course, just in one picture, a lot of discrepancies. So each reaction mechanism is maybe perfect for a specific condition, but is maybe not the best one for our specific condition. So you see large discrepancies here, NO as a function of time. But what you, for example, can see is here we have a lean mixture, phi equal 1, stoichiometric mixture, rich mixture. And what is interesting to see, the amount of NO reduces. And this is something, of course, we know this is what we have expected. So if you have slight rich mixtures, you get the minimum of NOx formation. Therefore, this is something, of course, we could expect, but we have to check, is the outcome we see here consistent with the literature, or have we done some errors? Here we have now, so in this example we have the high temperature cases over 2500 K or around 2500 K. So ignition is very fast. Here we are around 1600, 1700 K. So ignition needs much more time. And here, of course, you see differences not only in the maximum amount of NO, but also in the ignition delay time. Again, different reaction mechanism optimized for different configurations gives totally different results. And when we then plot, for example, here NO max as a function of temperature. So for all the simulations we have done, we have taken now NO max and plotted as a function of temperature for these three different mixture compositions. You can see big deviations comparing the mechanisms. So this is, of course, something we can expect, but this is something you have to do when you start with a new system. You cannot just take one mechanism and say this will work for me. First you have to check. You have to perform such simulations and then you have to analyze the results here, which one is the best for my configuration, or what we may see later. So after the break, what is necessary to optimize one of the mechanisms for your specific configuration. So when we come to the results here, so first of all, you have seen different mechanism gives different results, but all of them more or less shows the same trend. So from lean to rich mixture, we reduce the maximum amount of NO, which of course we can expect. And here we have also a plot for the ignition delay time, or the table for the ignition delay times when we change the amount of hydrogen in our mixture. And I just plot them here directly. Again, here we have different mechanisms, and here it looks much better when we compare them. And here you see the ignition delay time as a function of temperature for 5% of hydrogen, 10% of hydrogen, 20% of hydrogen. And what you can see, and this is what we would expect, if you increase the amount of hydrogen, the ignition delay time reduces. So, and finally, that was the idea behind this work for us, to use Cantera to calculate the ignition delay time using several mechanisms to learn more about the influence of hydrogen on the ignition of ammonia hydrogen air mixtures. And finally, just to complete this part, so HOMREA is the in-house tool I used in my PhD thesis already. It's just another tool to solve the equation system we have. And you see there are some small differences, but this is mainly due to numerical reasons. So we can use different tools. We do not have to use only Cantera. And finally, this was just a double check, is everything okay with Cantera, or have we done something wrong? So we get the same results, and so we were really confident with it. So now we have seen that we can use Cantera to perform simulations. That is very important to consider, do we have a proper reaction mechanism here, yes or no? And then we can use it, for example, to examine some fundamental changes in our parameters. So for example, what is happening if we add some hydrogen? Here we have focused on ignition delay time, but for example, you can focus on formation of NOx. So ignition delay time may decrease, which is maybe useful for our application, but also NOx formation can increase, which is then of course not useful. So these parameters you can easily examine without performing expensive 3D calculations in advance to find your optimum setup. And here we used it then further to examine the mechanism itself. So we used here quite simple sensitivity analysis. We want to examine how does the ignition delay time change if we change our elementary reactions. So we have a list of hundreds of elementary reactions, and if we change one of them, we just say the K value, the reaction rate doubles. How does this influence our system? Has it any influence at all? Does it change the ignition delay time, yes or no? And so, and here we use the simple relation. So the temperature, of course, when we look at this Arrhenius term, temperature is in the exponent, is very sensitive concerning the ignition delay time, is very sensitive concerning a change in temperature. So if we change the temperature, we change the ignition delay time, and in a way, so an increase of temperature decreases the ignition delay time. So that means here, if we change this parameter to change the temperature, it directly changes also the ignition delay time. So we looked here now on this sensitivity to get information about this sensitivity. For these mixtures here, again, argon mixtures with some amount of ammonia and oxygen. And so this is the outcome you get from such a calculation. You have normalized sensitivity here, so from 0 to 1 or from -1 to 1. And we just plotted here the most sensitive reactions. So we have for each reaction K, we have done this. We have compared the initial initial ignition delay time without any changes with the ignition delay time we yield when we change one reaction. And this is then the plot of the sensitivity. And here you see H plus O2 again, so my favorite reaction. So the ignition delay time is very, very sensitive, of course, concerning this reaction. But also we see here one specific ammonia reaction. H plus NH2 plus M gives ammonia plus M. So the system is also very sensitive concerning this reaction. And if it's positive here, so if we increase the reaction rate of this equation, it decreases our ignition delay time. And here we have an example, okay, if we increase this reaction rate, it decreases our ignition delay time. So that's a tool to examine more or less the reaction mechanism. We have thousands of reactions, but at the end we find 10 of them are important for our specific configuration. These 10 we need to know exactly. For all the others we can guess some rough numbers. Then the result is not depending so much for this specific configurations on them. So here we can optimize it. So this we have done for several here for the amount of, or the equivalence ratio. Again, my favorite equation, H plus O2, is in this list, and one specific ammonia reaction. And now we have just taken one specific mechanism here and changed the reaction rate in this specific mechanism, just to show you the result. So if we change the reaction rate here, of course, then we change the ignition delay time, and we have just done it very simple. We just multiplied it by a factor of 2. We just said, okay, this equation here is now 2 times faster than in the normal or given mechanism. And you see again, if we just change these 2 equations, you can see big discrepancies here. When you compare the modified model with the Shrestha model here. So NO max, you see a big change here. The maximum amount of NO is very sensitive concerning these equations, but also the position here, which then gives us the ignition delay time. So I would like now to make the break. I have explained to you how we can use quite simple numerical tools, so a 0D calculation, which gives us solution of the temporal development of our equation system within seconds on a normal personal computer, can be used to get very fundamental insight in our chemistry we are using. Of course, most often, if you are not interested in the development of your reaction mechanism, you are not looking on such specific parameters I have presented you. But very often, you just change your initial conditions, pressure, temperature, mixture composition, to find your optimum mixture configuration, which you then may use in a very complex, very expensive 2D or 3D calculation. Do you have any question until now? This I have shown you in the last lecture. So you can use different tools. So you have CH4 plus O2 gives water and carbon dioxide. That's the global reaction. And then you can do it based on experience. So you know, okay, we have CH4, we have oxygen. Okay, what are the possible intermediates? You can write them down. You get a list of thousands of species. And then you can say, okay, this is not important, this is not important, this is not important. So just try and error plus experience. So you can develop a mechanism, and then you can check it. Does it work or not? So, this is then supported now by quantum mechanical calculations. So for each of the calculations, you get detailed information then, or reactions about the activation energy and so on. We pay exponential factor. And nowadays, we do not do it by hand anymore. We can use something like this reaction mechanism generator. And you can look for this in literature. It's more or less done automatically. But then, of course, you'll get a very extensive list of reactions and species. And the art then is to optimize the setup. So does it answer your question? Yeah?
Sir, one more doubt. Is it possible to calculate the temperature of the product at last we get? Product temperature, reactant temperature and pressure we already know, initial condition.
Mm-hmm.
What about product temperature and product pressure at last we get?
So this Professor Zahu has explained tomorrow in the morning when you consider this adiabatic flame temperature. So the flame temperature depends on the initial conditions, pressure, temperature, and mixture composition. So I want to go to this list here. So we have not so much plots here. For each initial condition we have, we get the flame temperature here, for example. And I have shown you this plot temperature as a function of time. For example, there you can get this information.
To calculate the ignition time, so we are taking the OH radicals most of the time. So is there anything special about OH radicals? Why in maximum cases we are considering OH radicals?
Because it's easy to detect in the experiment. So H radical is much better. As I have shown you, there is an increase of, maybe I can show this plot again. On the left you see there's an increase, strong increase, and then it decays again. So it would be better, but it's much harder to detect. So for OH we can use chemiluminescence, so just measure the emitted light very often, and this we will learn maybe tomorrow or later. We can use specific laser diagnostics, so-called laser-induced fluorescence, and OH is very easy here. For H we have to use specific, very complex configurations. 2-photon laser-induced fluorescence, so it's much more complex. That's the reason why we use OH, because it's so easy.
My question is, so far what we have seen here is about liquid as well as gaseous fuels. What about solid fuels? For example, in big thermal power plants, they may use coals and woods. So is it possible to apply the software to analyze solid fuels?
I don't know it specifically for Cantera. I think it was done before, and you will find proper examples here. I have done it myself using another tool, but it's a simple one-dimensional setup. How can I try it here. So we have our coordinate, and we can say here we have our particle, our solid particle. So here we have gas phase, and here we have solid phase. And then the easiest solution is just to simulate the gas phase. So you can, for example, say here you have high temperature in the solid phase, and at the beginning the gas phase is quiescent and cool. So 2000 Kelvin, 300 Kelvin, for example. And then, of course, as a function of time, you see development of the temperature profile here, and after some specific time you see the ignition. So because for most of the solid fuels we have, the combustion takes place in the gas phase. So they vaporize, and then combustion takes place in the gas phase. There are very few compositions where you have direct burning of the solid phase. So that's the simplest setup. You define your solid phase, you define your gas phase, and reaction take place in the gas phase, and then you can also include some wall reactions. So the gas phase hits the surface, and something is happening then with them. And if you want, but you can also then incorporate reaction in the solid phase. Or if you have a droplet, you can have a droplet which evaporates, and you have reactions in the gas phase and the solid phase. Everything is possible with just one simple 1D calculation. Does it answer your question? Any further questions? Then we have lunch break.